Welcome to Easy Mathematics and a new video. Today I want to talk about a convolution. And before we start, so this video is for laymen and people who are interested in stuff like that, so I will not go through all details and I want to explain it not in a very rigor way, so this is for laymen. And yeah, but before we start, of course, we need some definitions. And yeah, before we come to the convolution, what is a sequence? And a sequence is, you can imagine that as an ordered list of numbers, and we denote a sequence in this way. A of I, where I is now in our case from the natural numbers up to 0, and this notation is for our list, so all the elements of our list are A0, A1, A2, ... And our numbers AI, they are from some certain definition set. This could be the real numbers or the integers or whatever, even functions if you like. In our case we deal with natural numbers, yeah, so in our case D are the natural numbers, also with the 0. Alright, and yeah, if we have a sequence, if we have defined a sequence, so our ordered list, it makes sense to play around with ordered lists. For example, how to sum up two ordered lists. And a quite natural idea is we add two lists so we add two lists and we make a new list out of these two if we add position wise. Okay, so AI plus BI is AI plus BI. Okay, so we take the same positions of the two lists and we add them up. And for the product, we create a new list CI of our two lists AI and BI in the following way. This is the sum k equals 0 up to I of AK times B of I minus K. And yeah, you see that the sum is depending on the position. Okay, and this crazy looking expression, this is what we call a convolution. And if you are not familiar with the summation sign and stuff like that, we write down the first few terms and then you get the idea. Yeah, so C0 is the sum from K0 up to I equals 0. So we have only one term. K is 0, so an A0 times B, 0 minus 0, so we have A0 times B0. C1, there are two summands. The first one is A0B1 plus A1B0. C2 is A0B2 plus A1B1 plus A2B0. And C3 is A0 times B3 plus A1 times B2 plus A2 times B1 plus A3 times B0. Yeah, so what you see is, so the indices of A, they are increasing 0, 1, 2, and the indices of B, they are decreasing, so from 2, 1, 0. Okay, and as you can see here, the sum of these two indices, K plus I minus K, is exactly I. So the sums of the indices should be the position of our new list. Yeah, so 0 plus 2 is 2, 1 plus 1 is 2, 2 plus 0 is 2. 0 plus 3 is 3, 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 0 is 3. Okay, so this is the definition of our product of two lists. And yeah, like I said, so this type of expression where the indices are running together, yeah, from the lowest position and the highest position, and then they run and against each other. Yeah, so this is maybe yeah, the imagination of the convolution. And yeah, before I want to show what I want to do, we can discuss two examples. So I'm pretty sure you know a couple of sequences, for example the sequence of natural numbers 1, 2, 3, 4, 5, or maybe the Fibonacci sequence 1, 1, 2, 3, 5, 8, or maybe the sequence of prime numbers 2, 3, 5, 7, 11, 13, and so on. And now we can apply our two operations, plus and multiplication. And like I said, for plus it's very natural to consider that we add the same positions. Like for example, if we add the Fibonacci list and the prime list, we get, so the first position of Fibonacci is 1, the first position of prime is 2, so 1 plus 2 is 3. Then the second position of Fibonacci is 1, the second position of the primes is 3, so 1 plus 3 is 4. And then we take the third, 2 plus 5 is 7, 5 plus 11 is 16, and so on. And for the product, yeah, so the zeros position, of our product list, we can see it here. We take the product of the first two elements, so 1 times 2 is 2. Then position 1, we get A0 B1 plus A1 B0, yeah, and so we have 1 times 3 plus 2 times 1, so 3 plus 2, 5. And then the second position, yeah, A0, B2, and so on. So we have 1 times 5, 1 times 3, and 2 times 2. So we have 5 plus 3 plus 4 is 12. And maybe we do the last one. Yeah, so the first one and the fourth one, then the second and the third, then the third and the second, and the fourth and the first. So we have 1 times 7, 7, 1 times 5, 5, 7, 5 is 12, 2 times 3 is 6, so 12 and 6 is 18, and 3 times 2 is 6, so 18 and 6, 24, and so on. Alright, so this is a small example of these two operations. And now what I want to do in this video is where you have seen the convolution in the elementary school. This is my claim. You have seen the convolution in the elementary school. You use it, yeah, nearly every day. You use a convolution. And where do we use this? We use the convolution if we multiply two natural numbers. And before I show you that, I clean up the board and then I come back. Okay, on the last board we discussed an example of the operations with two sequences, Fibonacci and the prime numbers. Yeah, and I said that the convolution appears in the elementary school, and I want to show where and yeah, where you use it in your, let's say, daily life. And yeah, I said also we use it when we multiply two natural numbers. And yeah, what do I mean by that? Let's say, for example, we have 17 times 34. Okay, how can we do this? Yeah, 3 times 7, 21. 1 carry digit, 3 times 1 is 3, plus the 1 is 4. Then 4 times 7, 28, 2 carries, 4 times 1 is 4, and the 2 is 6. Then we add them up. We get 488. Okay, but where is the convolution? Where here is the convolution? And it gets clearer. First we have to make clear that every natural number corresponds to a sequence in a certain sense. And as you know, we can write a natural number as a sum of powers of 10 and so on. Okay, so in this particular case we can write the 17 as 1 times 10 plus 7 times 10 to the 0, which is 1. And we have no 10 to the 2, 10 to the 3 and so on. So our sequence for the 17, let's write it maybe in this way. Our sequence for the 17 would be 1, 7, 0, 0 and so on. And the same game for the 34. Okay? And we see when we add two natural numbers, yeah, like the 17 plus 34, yeah, how do we add them? We add the 0 position, which is 11, so we have 1 carry. Then the position 10 to the power 1 we get by the sum of the two 10 to the power 1, so 1 plus 3 is 4 and plus the carry is 5. This is exactly this definition up to the carry, but I will not take care here of the carry. It's you can write down the carry, but it becomes quite messy and I do not want to take care so much about the carry. So here the addition of two natural numbers is exactly the same as our definition of the two lists. And yeah, as you can guess, our product is exactly this one. And to see this, let's say we have one natural number, let's say 10 times a1 plus a0, and a second natural number 10 times b1 plus b0. Okay, where the a1, a0, b1, b0, they are all from the set from 0 up to 9. Okay, but we forget about this for a second. And yeah, if we multiply them, we have 10a1 plus a0 times 10b1 plus b0. And now, which part of this product gives us the 10 to the 0 position? This is a1 and b0. So we get for the position 10 to the 0, we get a0 times b0. Okay? Then which part is for the 10 to the power 1 position? This is 10 to the power 1 times 10 to the power 0 and 10 to the power 0 times 10 to the power 1. So in other words, we have plus a0b1 plus a1b0 times 10 to the power 1. And this is exactly our C1, as you can see. And then our last part, so the 10 to the power 2 part, there is only one corresponding term. In this case, this is a1 times b1 a1 times b1. This part is here. And where are the other twos? I can write here, of course, 0 times 10 to the power 2. So a2 and b2 are 0, and all what is left is a1, b1. Okay? Times 10 to the power 2. Alright? Yeah, and what here happens is exactly this convolution, and what we have done here is exactly what we have written here. Okay, so let's check. So the 4 times 7, these are the two unit digits. This is exactly the a0 times b0 part. This is here. So 4 times 7, 28. So this is here the 8 with the two carries. And then we have the 3 times 7, so the unit digit and the 10th digit, and also here the 10th digit and the unit digit. This is exactly this part here. Yeah, so 3 times 7, this is here 3 times 7, so b1 a0, this is here. And then we have also the 4 times 1, 4 times 1, this is the 4 and the 2 in the digit, this is this part here, okay? So please pause the video and make sure you get this. Maybe you know also about the Indian multiplication. This is exactly what we have here. Maybe you know this with the Indian multiplication. If we want to multiply two numbers, two-digit numbers, we get we take the unit digits, 28, then with the digit on position 100 is these two in the product, this is 3, and then the middle part is this cross multiplication, so 1 times 3 is 3, plus 7 times 1 times 4, which is 4, and 3 times 7, which is 21, This gives us 25, and then we carry them up, so we results in 8, the 2 comes here, 27, the 2 comes here, 5. Where did I do a mistake? Something went wrong. 28, 3 times 1 is 3 times 7, 21, 4 times 1, 4, 25, 2. I guess I did a mistake maybe here. Yeah, you can correct me, please. I hope you get the idea with the convolution, and we use this since the elementary school. And now it's also clear, if we understand the convolution, it's also clear how we can use the Indian multiplication for 3-digit numbers. I've heard this question a couple of times. How can I use Indian multiplication with 2 3-digit numbers? And I want to show to you this also. So let's pick a 3-digit number, maybe 213 times 411 maybe. Yeah, then on the 0 position, we get the 3, 1 times 3. Then on the 10th position we get 1 times 1 is 1 and 3 times 1 is 3, so 4. On the so how do we get the thousandth position? The thousandth position we get with 10 times 100, 1 times 1000, so we have no thousand here, so we get it with 10 times 100, so we have 1 times 2 and 4 times 1, which is 6. And the 10,000 positions we get with 100 times 100, so 2 times 4, which is 8. This is the Indian multiplication, if you want to do it in your head. This is exactly the convolution what we use here, so please try it. I hope I did not a mistake here. Please try this convolution with the Indian multiplication. You will see that it's exactly the same. Also, like our method is also using the convolution. Yeah, and that's for today. I hope you like this video. See you next time, and bye bye.